My name is Henry Boateng, and I'm presenting on a research topic: performance evaluation of a flatbed maize dryer with a biomass heat source. This is a collaborated work done by myself, Henry Boateng, Mr. George Obin Akofi, and Mr. Joseph Akowa. Introduction: Maize. In Ghana, maize is predominantly produced by smallholder farmers who mainly rely on the open sun to dry their grains. And in securing their produce, these smallholder farmers combat a lot of challenges. These are some of the examples of challenges they undergo. The picture at the up left shows a woman spreading maize on a tarpaulin, and this depicts labor intensity and time consuming. Beneath it are some women stirring maize with their legs, and this depicts contamination. At the upmost right corner is maize being dried and soaked by rain, and this also depicts prolonged drying and gives room for fungus and mold growth. To curb these challenges, new modernized dryers have been introduced, but they are few and installed on gas or powered by diesel, which are very expensive to operate and not economically feasible for a smallholder farmer to patronize. So therefore, a newly fabricated maize dryer that utilizes biomass as heat source is being introduced and investigated. Objectives: the main objective is to evaluate the performance of a newly fabricated flatbed maize dryer with biomass heat source. Specifically, 1. To determine the operational performance of the flatbed maize dryer for drying maize, and 2. To determine the effects of drying temperature on stress crack and viability of maize grains dried using the flatbed dryer. Materials and methods. Study area. The drying experiment was conducted at Onsankom, a suburb of Techiman of the Bono East region, Ghana. Figure 1 shows an installed dryer with burner furnace, and this is a screw auger to convey the grains. Figure 2 shows a schematic view of direction of hot airflow. This is the burning chamber, and this is the heat exchanger. By conduction, as the heat exchanger gets heated, the blower sends the hot air, which are the red arrows, into the plenum, and it diffuses through the perforated mesh, which is the dotted line, into the drying chamber, and the red arrows as the heated air turn blue as it comes into combination with the ambient air temperature. Also, data loggers are hanged at the plenum to record the plenum temperature. And figure 3 shows the data logging points. Data collected is analyzed with a statistic package for social sciences and Microsoft Excel 2019, and the results are displayed in descriptive charts. These are some of the mathematicals used to determine the operational performance. Result and discussion. Figure 4 shows the plenum and ambient temperature variation versus time. You can see that at 10 o'clock to 10:10, both the ambient and the plenum temperature were having close temperature ranges at the 20s degrees Celsius, but at 10:20 the temperature leapfrogged from, as heat was introduced, it leapfrogged from the 20s to 60s. The plenum temperature recorded a maximum temperature of 73.4 degrees Celsius, and a maximum for the ambient was 27.9 degrees Celsius. An average temperature was recorded at the plenum to be 55.8 plus or minus 1.5 degrees Celsius, which was about twice the ambient temperature, which was 26.1 plus or minus 0.9 degrees Celsius. Figure 5 shows grain moisture versus drying time. At average drying temperature of 55.8 plus or minus 1.5 degrees Celsius and burner efficiency of 55.4%, 500 kilograms of maize grains were dried from an average initial moisture content of 18.4 plus or minus 0.1% wet basis to a final average moisture content of 13.4 plus or minus 0.4% wet basis in 5 hours. And also a drying rate of 1.02% per hour was achieved, resulting in a drying efficiency of 67.35% and a moisture extraction rate of 6.23 kg per hour. Lastly, to determine whether the temperature had negative effects on the grains being dried, a stress crack analysis was conducted, and figure 6 shows the percentage crack in grain samples. You will see that 73% of the seeds of the samples dried were uncracked. The single and double had 10% cracks, and the multiple had 7%. And this together gives us a stress crack index of 75%, which is low. Also, a viability test was conducted, and it was through germination test. We could see that 90% of the seeds germinated, which indicates that it was very good. Conclusion: I conclude that the 3-ton capacity of the flatbed dryer is suitable for a smallholder farmer. Its positive outlook in terms of its operational performance shows it can contribute to the drying needs of a smallholder maize farmer and help reduce post-harvest losses in maize at the smallholder level. Additionally, with no adverse effect on seed germination detected, the flatbed dryer can be suitable for drying grains for food, feed, and seed. Thank you. We want to express our sincere appreciation to the consortium for providing support for this research.